We saw earlier that for any measure space XS mu, we have that LP mu star was LP star mu where 1 by P plus 1 by P star equal to 1, and that is for 1 less than P less than infinity. So at that time we said that we are not considering the case of L1 which requires some measure theoretic arguments and so on. So now in the case of LP of omega we will prove this. So theorem. So this is also called a Rees representation theorem. Okay, so let omega contained in Rn be an open set. The dual of L1 of omega is isometrically isomorphic to L infinity of omega. Okay, so that means you can essentially identify L1 star as L infinity. Okay, so the proof we will do in several stages. So the first step, there exists W in L2 of omega such that for every K contained in omega compact, W of X is greater than or equal to epsilon K, which is strictly positive for all X in K. So how do we do that? So you so you consider En as usual like we did earlier. So only now you take annular. So set of all X in omega such that n less than or equal to mod X less than n plus 1. So omega will be the union of the Ens, n equals 0 to infinity. Okay, so and then you have you set W X equals alpha n strictly bigger than 0 on En, and choose alpha n such that sigma n equals 0 to infinity alpha n square mod En is finite. So you choose your alpha, so you know what the Ens are, you know their measure, so you then choose something like, for instance, alpha n can be 1 by n square mod n mod En. Okay, so that could be a thing which will give you something which is finite. Okay, so then W has the required properties. So because of this condition it is in L2, and then any compact set would be in some mod X less than or equal to n, and therefore it will have a finite alpha n's for each of them, and then you take the minimum of them. That will be a strictly positive number, and therefore you have that it will be positive on any compact set. Okay, so step 2, let phi belong to the dual of L1 of omega. So now you consider the mapping F going to phi of WF, F in L2 of omega. So what is mod phi of F? So mod of phi of WF is less than or equal to norm phi, norm WF in L1. Now since which is by the Helder inequality, this is integral mod WF, and therefore by the Helder inequality this is less than or equal to norm phi into norm W in L2 times norm F in L2. So this defines a continuous linear functional on L2. But then if you have L2 P equals 2, then this is also equal to P star, therefore L2 star is L2 itself, and therefore you have there exists V in L2 of omega such that phi of WF equal to integral on omega Fv dx for every F in L2 of omega. Because of the Rees representation theorem we have already shown for L2. Okay, so we have integral modulus of integral Fv dx over omega is less than or equal to norm phi into norm Wf in L1, which I already said is of course less than or equal to norm phi into norm W in L2 into norm F in L2. We have already seen this. Okay, so then next step, so you set u of x equals Vx by Wx. So W is never 0, that is how one of the conditions we saw. In the first step, Wx is strictly positive in every En, and therefore Wx never vanishes, and therefore this is well defined. So Vu is well defined and measurable. Okay, so claim U is in L infinity, and in fact norm U in L infinity is in fact less than or equal to norm phi. Okay, so fine. So assume, so let C be bigger than norm phi. Okay, and then you take set of all A to be set of all x in omega such that mod Ux is strictly bigger than C. Okay, so to show A has measure 0. So then essentially you will have mod Ux is less than or equal to C, and therefore the norm U infinity will be less than or equal to C for every C bigger than norm phi, and therefore norm U infinity will be less than or equal to norm phi. So that is the argument. So we have to show that. So assume the contrary. Then we can find B subset of A with finite measure, with finite positive measure. So if A has finite measure, then we can of course consider a subset of A which has still positive measure and which is also finite. A may be infinite measure, we don't know, so we want to show. So now you consider f of x to be equal to plus 1 if x belongs to B and mod Ux is positive, and Ux is positive, and minus 1 if x belongs to B and Ux is negative, and you have 0 if x belongs to omega minus B. Okay, so f is a bounded function. It is plus 1 is mod f is equal to 1 and on a set of positive measure, and therefore f is in fact in L2 of omega. and B has finite measure, since mod f equals 1 and 0 on omega minus B, B has finite positive measure. So therefore f is in L2. So we can use this f in our previous inequality here. Okay, so what is V? V is nothing now, u times w. So integral uwf dx, okay, is less than or equal to norm phi times integral wf in L1 is mod wf. Okay, now f is 0 outside B, so all the integrals come only to B, which has got positive measure, and then u times mod f, u times f is just mod u. Okay, so mod u w dx is less than or equal to norm phi integral on again B, because f is 0 outside, and mod w mod f. Mod f is less than or equal to 1, and therefore this is just mod w, and w is non-negative, and therefore I can just write w dx. But then what do you know about u on B? On B, you have B is contained in A, and mod u is greater than or equal to C on A, and therefore you can write this as C times integral w B dx. But then B has positive measure and w is strictly positive, and therefore this means integral w can be cancelled, so this implies C is less than or equal to norm phi, which is a contradiction because we have taken C bigger than phi. Okay, so we have taken C bigger than phi, and therefore C less than or equal to phi becomes a contradiction. Therefore you have that u is in L infinity and norm u infinity is less than or equal to norm phi. Okay, now step 4. So phi of wf, so for every f in L2 we have phi of wf equals integral v times f, integral fv on omega. But what is v? V is integral f times uw, because u is defined as v by w, so v is nothing but u times w. So now you take G to be continuous with compact support in omega. Okay, now then if you look at f equals G by w, now G is non-zero only on a compact set contained in omega, and on any compact set w is strictly positive. So 1 by w is bounded above, and therefore G is, so this belongs to L2. G is a continuous function on a compact set, and then 1 by w is bounded there because w is strictly positive over be greater than or equal to some epsilon k in that compact set k, and therefore this is, so we have k equals support of G compact. So w is strictly bigger than epsilon k, so 1 by G by w is less than or equal to 1 by epsilon k times G, and therefore this belongs to L2, and therefore G by w is also in L2. So we can substitute this in our equation, and therefore you get phi of G, sorry, equals, so f is equal to G by w integral fu dx. So there's a dx everywhere, which is understood, and sometimes I forget to write. Okay, so you sorry, this is not fu, it is gu, because fw is equal to g, so phi g equals gu for every so for every g in Cc of omega. And now we have that Cc of omega is dense in L1 of omega, and both the left hand side and right hand side are continuous with respect to G, both LHS and RHS continuous with respect to G in L1 norm. And therefore, so this implies for all G in L1 of omega, you have phi G equals integral omega gu dx. Okay, and mod phi G is less than or equal to, by the Hölder inequality, norm G 1 into norm U in L infinity, which is less than or equal to norm phi times norm G1. Okay. So now, so this implies that norm phi is less than or equal to norm U infinity. And we already saw in the previous step that norm U infinity is less than or equal to norm phi, and therefore this implies that norm phi equal to norm U infinity. So for every phi in L1 omega star, there exists a U in L infinity of omega such that norm U in L infinity is norm phi, and phi of G equals integral Gu on omega for all G in L1 of omega. Okay. Now we have to, of course, one more thing is that this is a well defined thing, and therefore step 5, such U is unique. Assume we have two. Assume U1, U2 such that norm U1 equals norm U2 equals norm phi, and for all G in L1 of omega, integral U1G dx on omega equals integral omega U2G dx equal to phi of G. So this implies for all G in L1 of omega, you have integral on omega U1 minus U2 G dx equal to 0. Okay. So so this means what? Now U1 minus U2 is, so U1 minus U2 is in L infinity of omega, so they are bounded, so on any compact set they are integrable, therefore they belong to L1 log omega, because they are bounded functions on any compact set as finite measure, and therefore it is integrable on, so this is in L1 log, and integral U1 minus U2 G dx equal to 0 for all G in L1, therefore in particular for all G in Cc of omega. And therefore by our previous proposition which we proved, this implies that U1 equal to U2 almost everywhere, that is U1 equals U2 in L1 of omega. So the mapping phi going to U is well defined. Okay, so step 6. So you take from L infinity, L1 of omega going to star to L infinity of omega. So U going to, let's say, Tu. So Tu of f phi going to U, where phi of f equals integral on omega U f dx, okay, for all f in L1. This map is well defined isometry and 1 1 onto. So it's 1 1 because it's an isometry, and it's also onto. Okay, and therefore you have that L1 omega star is isometrically isomorphic to L infinity of omega. So this proves the Rees representation theorem.